I was working in my office today and I came across this parabolic microphone and I got to wondering, what's the equation of the parabola and is the microphone actually at the focus of this parabolic microphone? So I took a picture of it, did a little manipulating to make sure I got it all centered up, turned just right, and I imported it. So now I'm going to add a function. So I'm going to add a function that is a times x equals y squared. And this is going to give me a slider. It's in terms of a for the parabola. Looks like I'm pretty good right here, but I'm going to let this play and see if I can get a different fit. So the slider's opening up. I could speed it up. I was right around 6. A little bit too wide. There we go. We're right about there. Okay, so that seems to fit right there. That's a good fit. So now this is an equation that fits. Now I want to find out if that conic has a focus right at the microphone. So let me make sure that I have my GSolve conics turned on. I'm currently set at decimal and normal, so I'm going to get answers all in decimal form. I'll change those in a minute. When I click on the parabola, I get lattice rectum, which is also known as my focal width, which is the length from one end of the parabola to the other end going through the focus. I get the eccentricity, which I'll explain in a minute. I also get the directrix and the focus. And that answered my question right there. One question was, the focus really is where the microphone head is. The directrix is also an interesting, and I'm starting to notice some things. The lattice rectum, or the focal width, is the same value as A. And this number, 1.4515, looks like it could be related here. From 15 to 6, that's almost a multiple of 4, I'm guessing, but let's see. I'm going to pull up a sticky. I'm going to take my value A, and my guess right now is it's A divided by 1.4515. Should give me a value pretty darn close to 4, if not exactly 4. Oh, it's exactly 4. So I'm starting to figure out that the value A, in this case, is telling me the length of the lattice rectum, and 1/4 of that value tells me the distance from the focus to the center and from the center to the directrix. Now there's another form of this equation that we have seen. We also see 4p. So 4p is another possibility for doing the same thing, and that's one you tend to see more often in textbooks. So let's see if we can make it fit and if it does indeed work. So let's move my slider. Notice this time the slider is growing faster because it's being multiplied by 4. So that's pretty good. It's not a perfect fit, but let's slide back a little. I'll press play. I'll stop it there. Okay, so now if my conjecture was correct, 4p should be the length of the focal width. So 4p should be the lattice rectum, and p should be the distance from the center to the vertex, to the focus, and the directrix. So sure enough, 5.7, 5.7, and focus, 1.425, directrix, 1.425. Now we also get this eccentricity. Eccentricity is an interesting number. Eccentricity comes from looking at conic section, which is two cones, one on top of another one. Let me center my picture. And it has to do with the ratio of sines. The sine of beta divided by the sine of alpha is 1. And what that means is that the section that is cut, like for example, if I cut with this line beta, the angle here is 58. I'm cutting this cone in two places. This is going to be a hyperbola. These are going to be ellipses. I'm going to get a parabola if I can get perfectly on 45. So when the angle beta is exactly the same as the angle alpha, you end up with a parabola. Otherwise, you end up with an ellipse, or if I come all the way down, a circle. So if you can imagine, these are conic sections that are being cut. An angle of 45, and both makes these parallel and makes, if you can imagine, on the cone, a nice parabolic shape. So now you can focus on the math by getting rid of your sticky, your background picture, and just choosing a value, and you should be able to tell everything you can about that parabola that has a p-value of 6.